Yeah, when I started looking at the labs, I knew they were in the drawer, but what I realized is there's two labs where the objects that we're using are not covered in the text. The two labs that we're going to do, I think they're 10 and 11, or 9 and 11, I can't write. I think the last lab, of course, is our troubleshooting. But two labs that we're going to look at, and I would like everybody probably to work on these today. Once you get through the lab, you have, wired up now or piped up now. We're going to look at counters and timers. And this is a pretty good write-up because there's a lot of stuff in here that we kind of touched on that we just don't have time to cover. So what we can do with pneumatics is we can do with pneumatics or fluid power about anything that we can do electrically. Some of the things that we do electrically is we do what we call logic, where we can say, okay, logic is the five basic logic functions are and, or, then, nors, and not. And believe it or not, all logic is done with those five basic ways. So counters, multiplexers, everything that you run inside a computer, all the logic that the computer has done is done with those five basic elements. So it's just like basically all the fundamental of all math is addition and subtraction. So we learn multiplication tables, but basically all multiplication is repetitive addition. But instead of me adding 5 to 5 times, we learned that 5 times 5 is 25. So the basics of just about all math is addition and subtraction. Square roots, division, all that we can do with addition and subtraction. So logic says, and says, if all the inputs are true, the output will be true. Or says if any input is true, the output will be true. Right? Or basically, in digital, it's a little easier to understand because we say highs and lows. But if you think of highs being pressure, then a low would be no pressure. So an and would say all highs to get a high, and an or would say any high to get a high. Nan would say all highs to get a low. A nor would say any high to get a low. And a not says a high end gives us a low out. So a low end would give us a high out, right? So basically a not just inverts that. If we turn that over to fluid power, we'd say all your pressure inputs are, all highs would be pressure, right? Then the output would have pressure on it. That would be a logic that uses fluid power using that. So this explains it a little better, and this gives us the symbols, and this gives us the actual logic symbol, and then this gives us the American National Standard Institute signal, or what we call the ANSI signal, which is the standard symbol that we should use. So this is air logic, and we do. And by the way, this gives the symbol, and we could pipe this up using just standard gates, just standard components. But logic has been around so long that now they made valves that do the logic for it. So instead of me trying to figure out how to pipe up regular, valves, pallet valves or whatever, and do the logic with that, and we can do it with units. So over there, I think in our drawer we got ands, we got ors, we've got those inside our box over there. One thing that the book mentions logic just a little bit. I think it was at the end of the first chapter. So here we got. Look at some of the things we can do. So we can do so this is an and, this is an or. An or is nothing but a shoulder valve. Because if any input on the shoulder valve has pressure on it, it's going to move to one side and put pressure out, right? I think we talked about that. We can do flip-flops. Flip-flops means every time I pulse the supply, the thing switch stays on that. And that's why I got the name flip-flop. We can do memory circuits, which means I'll put a pulp in it and it'll hold it until I'm getting ready to use it. Then these are the ones we'll look at here. One shots means we give it a pulse. Even if we leave it pressure on there, we put pressure on it, the output will go true for a certain amount of time, and then it automatically switches back, no matter how long we leave the pressure on there. So that's one shot. So if you're in electronics and you take digital, we'll do that. But this is the one we're going to do in lab, and this is what we have. We have timers. So what do we need timers for? Well, in timers, we do a lot of things with timers. In other words, we come up and we push something out with a cylinder, and then we have to wait a certain amount of time before it clears. Well, instead of me sitting there and looking at it and trying to say, okay, is it clear? We could just put a time delay in there, right? You understand? So when it pushes it out, it waits a little while before it does what? Before it retracts, or vice versa. So we have two basic timers. We have what we call on delay timers and off delay timers. So this is a symbol for a timer. This is the logic symbol. This would actually be the ANSI symbol. So which one you use is up to you. I think this would be pretty easy. Anytime we see an arrow through this, it means it's what? It's variable. So we'll come up here and we'll look at our timers. And then what we'll notice, I'm sorry I didn't shut my camera. I'll pass it around. The first thing we'll see is we'll see that each one of them's got a little knob on it. Now, if you don't have the arrow through it, it means it's going to be preset. So it'll be like 5 seconds or something like that, and you can't change the time. The only difference between the symbol is it won't have the arrow through it. If it has the arrow through it, or the slanted arrow through it, what does it mean? It means it's variable, so you can set the time. Unfortunately, we don't have any off delay timers. All our timers are on delay timers. So on delay timer means we put pressure on it, and then after a certain amount of time, the output's going to do something. And the two timers that we have is we have a normally open timer, and we have a normally closed timer, but both of ours are on delay timers. And this is where, and the way the lab is set up, I'm not really sure if it's set up to use the on delay timer or the off delay timer. I mean, I'm sorry, the normally open or the normally closed. Oops. I got 3 different cameras I hook up to these things, so I got 3 different applications. I used the wrong one that time. So this is one of our timers. If I can get it. Good gracious, I'm zoomed in. Where's it at? Right here. So you see right here is a little watt, and I'll pass this around. Here's a little adjustment where we can come here and set the time. The time's in seconds, so this gives us an indicator of what's the time. And these are our 2 ports right here. So 1 would be the pressure port, and 2 would be the output. But what you'll notice is when 1 goes true, we put pressure on it, it's going to be a watt. It's going to be a time before 2 actually outputs the pressure, which is pretty neat. This right here is normally closed. I don't know if my camera will focus in on that or not, but like I said, I'll pass it up. But when it's drawn in its normal position, you'll see that one, which is the pressure port, is blacked off. So this would be a normally closed timer. The other timer that we have is black. This is a normally open timer. So the only difference within the symbol is you see one is shifted to 2. So anytime this happens, so what this guy's going to work is this is going to put pressure on the valve. So if we were extending the cylinder would be extended. And then after this times out, it would do what? It would retract. Okay. That makes sense. And it's only timed in one direction, so that means as soon as you turn it off, it should do what? It should go back. That timer, which is a normally closed timer, if its normal position was retracted, then after a time it would do what? It would do it. So this is a normally open on delay timer. An off delay timer will start timing when you remove pressure from the control. So it's got to have something in there that stores charge. So it will definitely have to. So what I'm gonna do is show y'all. This guy's pretty cool. This is a video that I found on the internet.
So these are only 30 seconds?
That would be the maximum on this one. But what you got to understand is that you buy timers that give you different time delays. So you could buy them in minutes, or if you needed 60 seconds, what could you do? You can double up, so you can take the output of this timer and do what? Feed it into another. And depending on what you wanted the second one to do, the first one would be a normally closed, right? You understand? But your second one would be what you want your timer to do. So we could use multiple timers and get a longer delay, or we could buy a timer that gives us a better option. So you're right; these are 30-second timers. So even when we buy timers for electrical timers, so timers are something that's very important in control, right? You understand? Like having things delay, having things wait. We have a big problem with electric motors is that they have what they call an ingress current or a starting current, which is 6 to 8 times their running current. So you get out there and you fire up your line at the same time and you start 20 motors at the same time, you're talking about a massive inlet current. So a lot of times they'll do is they'll time delay, they'll stagger start the motors. They'll start one and after time they'll do what? They'll start another and start another. You'll see that all the time. You prevent that massive inlet when we're trying to start a bunch of motors at the same time. So timers, we use timers all the time. Of course, if we're running solenoids and stuff like that, then the PLC can do the time for us, right? You understand? But if we're running a totally pneumatic system, then we need to have the ability to do this also. So we have pneumatic time, and that's what we're passing around. That's what we're passing around here. So this is a pretty good video. I didn't find a video on the counters, but these guys are fairly simple. Well, they're easy for me to understand. I don't know about y'all, but so this PowerPoint's not on there, and the link wouldn't even be on there anywhere. But I'll put the link up there for you, so if you want to go out and look at it. So y'all gonna have to listen because we don't have a set of speakers in here. So see if y'all probably need to.
All right, guys, lab number 12. Now we're getting into some interesting stuff. Anything you can do electrically, you can also do with pneumatics as well. You want to make an on-delay timer, you can definitely do that. You just need a few components, similar to what you have in a standard electrical timer. The components that I'm going to show you are similar to a resistor and a capacitor. Resist the flow to the capacitor gets to a certain voltage, and then sends a signal to turn on. Same thing we're going to do here. We're going to have a flow restrictor with a holding tank, and the holding tank is going to act as our capacitor. Okay, let's take a look at the circuit and what we're being asked to do. Use a 3-2 push button and a 5-2 pneumatically operated spring return relay and a double acting cylinder. Okay, so push button controls a 5-2 pneumatically operated relay, and that relay then controls our double acting cylinder. Provide a delay on signal circuit in which you press and hold your 3-2 push button, and then after a 5-second delay, the 5-2 relay is going to change state. When the 5-2 changes state, the double acting cylinder is going to extend. As soon as you let go of the push button, the double acting cylinder is going to retract immediately. So it's exactly the same as an on delay timer. Press and hold the start circuit. It takes a little bit of time before it changes state. As soon as you let go of that signal, it reverts back to its rest state. Okay? If you're Googling this, you will find that they'll come up with this diagram here. Very similar to what we're going to do. But again, we do not have 3-2 pneumatically operated valves. We're going to replace this 3-2 with the 5-2. Okay, let's take a look on the fluid sim. Alright, so let's build this up nice and slow. We need to have one of these signals coming in. Let's do the rest state as a retract. Right, so here's our main compressed air coming in. And in the rest state, being denoted by this spring, air would come up, push this guy back, and then we just need a path for that air to exhaust out. Looks good. We're also going to provide our 3-2 with some air there.
You have to understand.
Okay, looks good.
It's always better.
I think if I could drop this down, otherwise you're going to have superimposed lines. We'll see how it works out. Okay, so we have the 3-2, and now the signal going into our 5-2, we're now going to create a timer using two components. We need to have a holding tank, and we also need to have a flow restrictor. So let's drop down here. The flow restrictor is right here, the one-way flow control valve. Okay, and let's see if this guy is going to work. Let's see, right here. Looks good. We'll move this bad boy over here.
He's got an accumulator up there.
And we'll move this guy over. Looks good. Alright, so you can see that we have a one-way flow control valve. We have a holding tank. And this portion is going to be in our signal going into our 5-2. Okay, I'm going to tie in.
So how do you think this is going to work? So he's got an accumulator right here. Let me get a little further. Get a little. Yeah.
This guy right here into this part of the circuit. There we go.
So we've got it made.
And the way that I'm going to...
So tell me how you think this is going to work. So when he shifts this valve over here, down at the bottom, it's going to put pressure through the flow control. The flow control, since it's at the point, it's going to seat the check valve, and it's going to have to go through the flow control. Then we got this big old empty tank over here. Got this big old empty tank over here. So that means it can't generate any pressure on it to shift that pilot valve, that pilot operated valve over there until that accumulator fills up with pressure. As soon as the accumulator fills up its pressure, then it's going to, then the pilot operated valve is going to shift up. So what we're doing is we're controlling that flow control valve. So the more restricted I make, the longer it'll take to fill up the accumulator. The longer it takes the accumulator, the more time it takes to create enough pressure to shift the fluid in that valve. Now, when I turn it off, it's going to open up the check valve, and it's going to dent instantly, right? You understand? So what's going to happen is that when I press that button, when he presses this button over there, it's going to not shift instantly. It's going to do what? It's going to wait a little time, and then it's going to shift. And then he's going to let it go, and it should do what? It should return in. But we'll see if the simulation will take a little while. There is no time delay. If we pipe this up in the class over there, we find out that it would be no time to retract. The time would be on what? On the extender.
Describe this is this is our restrictor, and this is our resistor, and this is our capacitor. So we're going to create something similar to an RC circuit, in that this resistor is going to limit the flow to our capacitor. Once the capacitor gets to a certain pressure, then the signal is going to travel through to the 5-2. Okay, this is a one-way flow control valve. We can change this to an off delay by flipping this component around. Remember, this is like a check valve with a flow restrictor component in it. Okay, so let's hit play and see what happens. Excellent.
Well, not
Okay, so we have the air coming up in the rest position. It's in the retracted position right here. And then hitting this push button will allow the air to come up. It will seat this ball. We'll have to go through this flow restrictor. That flow restrictor will determine how fast this charges up. And then remember, this is a closed circuit, so any pressure that's in this tank will also be in these lines. That pressure has to build up to a pressure that's greater than the spring. Once it's greater than the spring, the 5-2 will change state, and this will extend. So now we haven't changed the flow restrictor whatsoever. So it's wide open right now, and if we hit this push button, change the state. Okay? So it took 1 or 2 seconds there in order for it to change state. If we want it to be a little bit slower, then, and you can see that it looks like we have an on delay and an off delay on this guy. So that's the issue with this simulator, is that we're trying to show an on delay timer, but by changing this value right here, sometimes the simulator isn't going to work exactly how like we'd have out in the field. So let's double check. This is open 100%. So let's bring this down to maybe 25%, and we'll see how that affects our circuit. So we're going to hit this push button, builds up pressure, then eventually when that pressure gets to a value that's greater than the spring, then it changes state right away. Excellent. Now when we let go of this push button in the lab, that double acting cylinder is going to come right back. Let it go here in the simulator, it takes a little bit of time. So there's no way around that in the simulator, not that I know of. If you do know a way to do this, then put it in the comment section.
So everything that we've got is built into the timer, right? So instead of us having to build the circuit, we have a unit there where all the emulator and everything is built inside there. So we have one symbol, but we could build it out of what we call, in electronics we call it discrete components. So I could build a computer out of discrete components, but it would probably take us a while, because right now we have over 1 billion transistors inside it. But eventually, when these things first started off, they were built with discrete components, right, before they started integrating them into a package. So that's basically an on delay timer. The one that are those out there? If you notice, this one only has 2 ports. So this guy here is a normally closed. What he's got right here is a normally open. It's a normally open position. So notice here, the way it's hooked up, the cylinder is started off retracted. But if you wanted the cylinder to be extended, all you'd have to do is change the pipe. Okay, you understand that? The black one, if you look at the black one, it's got 3 ports. So the way this one works is we have a pressure port. We put pressure on one. The output would be 2, and then we time it with 10. Okay, does that make sense? So normally closed, the normally open, we put pressure up all the time to this one, and we time it with 10. The normally open is when you put pressure on one, then it'll start timing before it goes to 10. So we have 2 different options. So the normally open is a little different than the normally closed. And I don't know which one the lab is set up. We'll see that.
On the road is closed,
You could, but it's already blocked off, so you don't really need to. I don't know. This don't even show a 10 on it,
right,
on the cylinder. So I'm not sure if it's piped inside there or not. Okay. So,
that's our final lab.
no, our final lab is a troubleshooting lab. We're going to work on this weekend. So you're going to have an assignment this weekend. So what the last lab is, and we'll do this on the last 2 classes, is is we're going to let you design a circuit. And then what's that? So that's what you're going to do this week. You're going to design and file a circuit. You decide what it needs to do. The only specifications that we have on that lab is that you have to use at least 2 directional control valves and 2 actuators. You design the circuit, right, and send that. And then what you'll do is you'll come in and you'll pipe it up, and then you'll write down, you'll check to make sure it operates the way you want it, and you write up the detailed operation. So we'll bring the class around real quick and let them look and see your circuit operating, and then you're going to put those in. And then what's going to happen is the class is going to try to troubleshoot or figure out what's wrong with the circuit. And that's the last lab. That's the lab of that one.
So this is what, 5, 12, 9, or 10?
It's the next 2. I think 8, 9, 10, 11 is the last lab. Yeah, 9 and 10. 9 is the timer. 10 is counter. And 11 is design. So the counters are, the problem is that I couldn't find any YouTube on counters, but it's pretty straightforward. We can have what we call a down counter and we can have what we call an up counter, but this is, ours are all down counters. Well, we only got 1 counter in there. And I don't think this right here, let's see if it covers counter. So the counter, we have 4 ports on. We have Y, Z, A, and P. So what do you think P would be? Pressure. So what's some of the things you might want to do with a counter?
We'll probably want something to come back a certain amount of time before you use the air pressure to keep it out.
Well, a counter is going to be, it's going to count, right? You can understand why a counter would be very important. A lot of my business has to do with how many bad parts I have, how many good parts I have, how many I run during the day, and all that kind of stuff. But one of the things that we constantly use is counter. And it depends on, so I could have a cam operated valve over here, and every time a part comes by, it increments my counter. But the problem is, I have this counter set up at the end of the day, it's got 200, and what would I probably want to do next? I probably need to have the ability to reset it, right? Does that make sense? So we probably got a reset on it, we probably got a pressure on it, we probably got a count on it. And let's see what else we have. So what I'm gonna do is just go on the internet and look up pneumatic counters. No, this is all this is just the specifications, right?
Alright guys, lab number 12. Now we're getting into some interesting stuff.
I'm going to log it into my computer in my office over there, because this is where I looked it up at. So ours is what we call a down counter. Y'all know what that would probably mean. So we'll set a value in it, right? And then every time it gets a pulse on the input, it should do what? It's down there. And then when it gets down to 0, it's going to generate a what? An output, right? So here, the P is the watt, pressure, Y is going to be the watt, reset, Z is the watt, output, and 2 would be the watt. We're about to figure out what that is. So here we don't have a 2. We got an A, we got a P. They don't have a symbol on it. So we got an A, we got a P, we have a Y, and we have a Z. So A, P, Y, Z. What do you think? The only one that's missing from this tutorial is 2. Would be what? PA. Okay, so A would be the output, right? Okay. Y is going to be the what? The reset. So if we count that, whatever we pre-rolled it with, like 5 or 6 or something like that, it should be what? Should reload it, I think. I'll have to look at that. P is the pressure source, Z is the output, and A would be the count input. So every time we pulse A, whatever we're pulsing it with, this counter should count down, right? And when it reaches 0, it should do what? Generate an output. Everybody okay on that? Yes or no? This looks like it might have a reset button on it. We'd have to figure out which one that is. Are we okay? We'll put this up over there. We don't have I wish we had a little compressor. So that should get us up on our labs. Y'all got any questions about anything else before we go lab? So let's look, make sure we look at the course calendar to make sure. So what I want y'all to do is
we have time for you work on something else?
Yeah. So what we're gonna do, to start off with, let's go ahead and spend time with the timer and the counter lab out of the way. And then what you can do is you can drop back. Then we've got, during the weekend, what you're gonna do during the weekend, I'll put an assignment out here. You're gonna design your circuit to do what? And the only specifications on the circuit. Got to have these 2 actuators and 2 control valves, right? Okay. We're going to design your circuit, and then what are you going to do Monday? We're going to come up, we're going to pipe it up, right? So today, once you get through with these 2 labs, the rest of the day, you can go back and try to pick up on the labs that you had got done, right? And then next week, well, let me go back and let me double check. Let me bring up the course calendar. So I think we got 2 days next week for we might shift it a day. We might give y'all next week to so our test. So test 3, we're right here. So we got today, we got Monday, Wednesday, and then, this Monday, we're gonna have test 3. What we're gonna do for test 3, guys, is gonna be a little different. So normally what we do is we give our test at the end of class, and then the next class we go over the test. What we're gonna do on test 3 is we're gonna give the test first. If you're late, you're just not gonna get enough time to finish it. That's not my problem. But that way, we have time to see if there's any problems with the test and we can go over it before y'all do the final exam. The other 2 tests are out there. If you're gonna wait until test 3 to start studying for the final exam, you're not gonna have time because test 3, the next class we're having the final exam. So what should you start doing right now? Yeah, the only thing that the final exam is just test questions off the other 2 tests. Now, off of test 1, we're gonna do it on computers, so I'll probably make those multiple choice, so they might be a little different, but they'll still be the exact question. The key is out there for a test 1. Test 2, you don't have the key, but what it does is it shows you which ones you missed, so you can go back and figure out what you did wrong, right? Does that make sense? So you should start doing that now. And then when test 3 rolls around, the only thing you'll have to study before the final is just 1 test, right? That makes sense. So here we are today. We're going to be in lab today. Then we'll be in lab Monday. And what are we going to do Monday?
Go over.
Yeah, so what you're going to do this weekend at home, you're going to do what? You're going to design your circuit. So what I'm going to do when I come in Monday, the first thing I'm going to do is I'm going to look at your circuit. So if you don't have your circuit designed, then you're going to get a 0 for that assignment, right? You understand? And then you're going to have to design your own circuit, right?
I got bring in mind this. I got drill.
In next weekend?
This weekend, the 2nd and 3rd.
Well, that won't prevent you from designing the circuit. You have paper. Well, you have paper available.
Yeah, but
I
guess it's like
sure.
working a job. Like working a job.
Well, it's college.
Yeah.
Okay, you understand?
Yeah.
Okay. So I don't know what you want me to do. This is required Monday.
Oh, no.
It's up to you whether you want to do it or not. That's your call.
No.
I mean, that's what I'm saying. You got access. Y'all have access to the internet, as far as I know. Even if you don't have access to the internet.
That's so design. I mean, as long as we design it and set up on paper, if it's not perfect, we can still adjust fire, right?
Yes, sir. That's right.
Okay. I was looking at the time.
So what you're going to do is you're going to design it. So if you come up here with a crappy piece of paper that's got
No.
stuff all drawn on it, right? There's no chance in the world that it's going to work. I'll probably be a little upset.
No.
I mean, I appreciate what you do. I really do as far as going to that, but I understand. We had a guy that had to go to Kuwait. He still finished the course. And what we did, his staff sergeant would proctor him when he took his test. So he took his test, sent all his work by email, and he was over in a war zone.
Still finishing school. I bet you.
Well, no, he finished that semester. He's still over there, guys.
I bet you.
He's a really.
I bet you he looked forward to his last work time. I know I would if I was over there.
So yeah, he was deployed during and there's nothing we could do. You know, it's the military. So.
Right. They don't really say, hey, come when you can. No, come now.
So what branch? Oh, he's already gone. I was going to ask him what branch is he in.
I wish I could. There's some days I wish I could.